My name is Eleanor Sigrest, and I'm a senior at Forest Park High School and the Governor's School at Innovation Park. Ever since I can remember, I've wanted to be the first person on Mars. I realized if I wanted to achieve my goal, I needed to help out. So I started researching, and I found a problem that has plagued NASA since the 1950s. Slosh. Slosh is the unwanted movement of fluid in a tank, and it has caused many problems, to include spacecraft jitter, which is the unwanted movement of a spacecraft and can lead to mission failure, such as the Apollo 11 landing, inaccurate fuel gauging at low fill fractions, an increase in weight through extra fuel and additional slosh mitigation subsystems, and an increase in system complexity. Current solutions, such as propellant management devices, or PMDs, have cost billions of dollars just since the 1980s and are ineffective and inefficient. Slosh in microgravity is governed by cohesion and adhesion between the fluid and the tank. This made me wonder, can I mitigate slosh by using custom surface energy profiles inside of the tank? The premise of my experiment was to coat the inside of the tank with a coating that pushes the fuel from where it's not wanted and a coating that attracts the fluid to where it is wanted and encourages it to settle there. From there, I created two hypotheses. First, a selectively coated tank will aggregate more fluid around the fuel sump than compared to a tank with no coatings. Secondly, a coated tank will have a faster settling time than a non-coated tank. I chose water because it was easily accessible, safe, and had similar properties to hydrazine, a commonly used rocket fuel. This allowed me to use superhydrophilic, which means it really likes water, and superhydrophobic, which means it really dislikes water, coatings to produce my custom surface energies. I have three coating profiles: 80% superhydrophobic, 20% superhydrophilic, 50% superhydrophobic, and 50% superhydrophilic, and a no coating to serve as a control. I replicated my experiment at different fill fractions and with and without PMDs. Testing different fill fractions is important to see how the custom surface energies will affect the fluid behavior over the life cycle of the tank. It is essential to test with and without PMDs to see if I can eliminate the need for PMDs, thus reducing unnecessary cost, complexity, and weight, and increasing mission capabilities. I flew my experiment on a zero-G parabolic flight to achieve microgravity through parabolic arcs. Each parabolic arc created about 15 to 22 seconds of microgravity. Through GoFundMe, grants, and working a job, I raised $25,000 to pay for flight services, fees, and other costs. The size of my tanks was critical because the bigger the size, the more scalable the data, but the bigger the tank, the longer it takes for the slosh to settle. By using equations from the literature, I found that a 1.5-inch inside diameter was the biggest size of the tank with a predicted slosh settling time within the 15 to 22 second microgravity period. The fluid tanks are acrylic spheres, which allows me to see the motion of the fluid while only having to worry about acceleration in one direction. The PMDs were simulated using circular pieces of acrylic. The test apparatus has slides to impose a linear acceleration on all the tanks simultaneously. The data collection subsystems consist of a master Raspberry Pi that sends start and stop signals to 12 follower Pis. Each Pi has a Pi camera to record 2 tanks, which allows me to analyze the data after the flight. The flight consists of 20 parabolas. Panels H through K show the fluid aggregation data. The control tanks performed as expected, creating a sphere with a bubble in the middle, or wavy surfaces with bubbles. Bubbles increase the risk of air entering the engine and causing misfires or no starts. The coated tanks settled in pyramid or flat shapes, which prevented bubbles from being trapped in the fluid. I concluded the non-coated tanks settled at the sump 12% of the time without a PMD and 64% of the time with a PMD, while the fluid in the coated tanks settled at the sump 100% of the time. The average settling time decreased with the coated tanks compared to the control tanks. The 50-50 coating profile performed the best overall because its average settling time was the least. This proved my solution can improve or totally eliminate the need for PMDs, which can save NASA billions of dollars. Due to the impact of my research on the space industry, I plan to drive this capability to further technology readiness levels, or TRLs, through a series of follow-on experiments to scale the results in microgravity periods, collect data to support a computational fluid dynamics (CFD) model, and investigate conformal tanks and ultra-high wetting fluids like cryogens. I am currently under contract with Blue Origin and have an upcoming suborbital flight on New Shepard to increase the microgravity period. In parallel, I'll start developing a technique to create fuel-compatible surfaces inside of fuel tanks. In conclusion, my experiment decreases slosh settling time, improves fluid aggregation, and eliminates the need for PMDs. This decreases the overall weight, complexity, and cost of spacecraft so we can carry more payloads, learn more about space, and send more missions to the stars for the same cost. My technique is needed to send humanity to the stars and beyond. Thank you so much for your time. Have a wonderful day. Bye.